Metal carries electricity better than air does. That is why the wire inside your wall is copper, and why nobody runs a circuit through an empty room and hopes. But at the top of some of the tallest towers in Dubai, that ordinary fact has been turned into a piece of architecture. The building does not end in a roof. It ends in a steel needle that has been deliberately built to be the easiest path to the ground for miles in every direction. A charge gathers in a storm cloud over the Gulf. It reaches downward, feeling for the shortest route. The steel at 2,700 feet finds it first. The current runs down the frame, through the concrete core, into the foundation, and out into wet sand. At first, this might just seem like a solved problem, and in one narrow sense it is. But the same needle that makes the lightning safe is also the part of the tower nobody can reach, the part that moves the most, the part that gets the hottest and the coldest, and the part that no window cleaning machine in the building was ever designed to touch. So what actually happens to 4,000 tons of steel that spends 15 years being struck, heated, cooled, and shaken at the top of a desert skyline? And why is the greater long-term problem almost certainly not the lightning at all? You have watched a photograph of a tower with a bolt of light coming out of its top and thought that the tower was the victim. It was not, it asked. That invitation is the subject of this video. Most people looking at a super tall tower stop reading it at the point where the windows stop. Above that line, the shape narrows into something decorative, and decoration is not where anyone expects engineering to live. To understand the top of a tall building, you have to stop looking at it as an ornament and look at it as a separate structure that happens to be standing on another one. The Burj Khalifa opened in January 2010 and stands 2,717 feet tall. According to the figures published by the tower's own operator, the Spire is more than 200 meters of that height, which is over 650 feet, and it contains more than 4,000 tons of structural steel. 650 feet is not a finial. It is taller than most buildings in most cities on Earth. It is roughly the height of the Washington Monument, sitting on top of something else. And it was not craned into place. There is no crane that reaches that far. The spire was assembled inside the building and then pushed up through the crown from within, using hydraulic jacks and side guides, in a sequence of 8 separate lifts, with the whole assembly climbing out of the tower like a telescope being extended. Every section had to be welded and bolted by ironworkers standing inside the crown, in a space with no room to swing anything, while the tower around them was already finished and occupied below. That construction method matters for everything that follows, because it means the joints in that steel were made in a confined space at 600 meters, and they will never be made again. What follows is that structure being taken apart, one piece at a time. This channel exists to take apart the parts of enormous buildings that nobody ever looks at. So if that is what you came for, subscribe and stay with it. Start with the lightning, because it is the part everybody asks about. The National Fire Protection Association publishes the American Standard for Lightning Protection Systems, NFPA 780. The International Electrotechnical Commission publishes the international equivalent, IEC 62305. Both describe the same 4 elements: an air terminal that takes the strike, down conductors that carry the current, a bonding network that keeps everything at the same potential, and an earth termination that puts the charge into the ground. The tower's operator describes exactly this arrangement. A specialized rod at the peak, designed to take the hit, a network of metal conductors down the exterior, the steel frame acting as the pathway, a grounding system dispersing the charge into the earth. The design principle underneath it is older than any of these documents and is usually taught as the rolling sphere method. You imagine a sphere of a fixed radius rolled over the structure. Wherever the sphere touches, lightning can strike. Wherever it cannot touch, the structure is shielded. Raise a tall enough terminal and the sphere never reaches the roof at all. So a super tall tower is not accidentally the target. It has been engineered into a target on purpose, because a strike that lands where the engineers put the metal is a strike that does not land anywhere else. This is not new. The Empire State Building opened in 1931, and its mooring mast, built for airships that never used it, has been absorbing strikes ever since, on the order of 20 or more in a typical year. The engineers there worked out the same trade 80 years before Dubai did. The same logic is visible on One World Trade Center, which opened in 2014 and ends in a mast rather than a roof, and on the Ostankino Tower in Moscow, completed in 1967, which is largely a slender vertical structure and very little else. Whenever a designer puts something tall and thin at the top of something tall and wide, the thin part becomes the lightning terminal, whether it was drawn for that reason or not. The lightning, then, is handled. Now look at what is not. Current is only one of the things that arrives at the top of a spire. The second is wind, and wind treats a slender steel needle very differently from the way it treats a concrete tower. A wide building resists wind by being heavy and stiff. A narrow one cannot. As air flows past a slim vertical member, it does not flow smoothly around it. It sheds swirls alternately off one side and then the other, and each swirl pulls the member sideways. Engineers call this vortex shedding, and the American Society of Civil Engineers deals with it in its loading standard, ASCII 7. The important part is the word alternately. Vortex shedding is not a push, it is a rhythm, and the rate of that rhythm rises with the wind speed. At one particular speed, the rhythm lines up with the natural frequency of the steel it is pushing, and the small sideways pulls start to arrive in time with a motion that is already happening. At that point, the tip does not simply lean, it whips. There is a second complication that comes from the way the thing is built. The concrete tower below has one natural frequency, set by its enormous mass. The steel spire above has another, much faster one, set by its small mass and its length. Two oscillators of very different character are bolted together, and the joint between them is the place where their disagreement has to go. The engineers who did the wind tunnel work on these towers were not designing against a storm. A storm is straightforward, because a storm is a large force, and large forces are what structural engineering is best at. They were designing against an ordinary breeze that happens to arrive at the wrong speed and stay there. The third arrival is heat, and this one is relentless in a way the other two are not. Steel expands when it warms. The coefficient is small, about 6.5 millionths of its length for every degree Fahrenheit, and in a beam 10 feet long it is invisible. In a member 650 feet long, across a swing from a winter night to a summer afternoon of 90 degrees Fahrenheit, it works out to something close to 5 inches. 5 inches of movement, appearing and disappearing every single day for 15 years and counting. Nothing about that is dangerous on any given day. The structure has expansion allowances designed into it precisely for this. But steel that flexes through a cycle is steel that is accumulating fatigue, and fatigue is the one form of damage that does not care how strong the material is. It only counts cycles. 15 years at roughly one full cycle a day is somewhere around 5,500 cycles, which sounds like a small number until you remember that the structure is expected to stand for a great deal longer than 15 years. A 100-year design life on a daily cycle is more than 36,000 of them, and the fatigue curves that engineers use are drawn on a logarithmic scale precisely because the numbers get large quickly. There is also the sun itself. A vertical member catches direct sun on one side and not the other, so the two faces are at different temperatures at the same moment, and the member curves very slightly toward the cold side. That is a daily bending cycle on top of the daily stretching cycle. In a desert climate, the temperature difference between the sunlit face and the shaded face of an exposed steel member can run to 40 or 50 degrees Fahrenheit in the middle of the afternoon, which is a larger gradient than the same member sees between one season and the next in most of Europe. Then add the air. Dubai sits on the Gulf Coast, and marine air carries chloride. The American Concrete Institute has documented for decades what chloride does to steel embedded in concrete. But bare structural steel in a coating system is exposed to the same chemistry with fewer defenses. Coatings on structural steel are usually specified against standards such as ASTM A123 for hot dip galvanizing, and the welds themselves against AWS D1.1 from the American Welding Society. Those systems have design lives. They are measured in decades, not centuries. So the question is how anybody knows what condition that steel is in. And here is where the honest answer becomes uncomfortable. The building maintenance units that carry the facade cleaning cradles are designed for the glass. The tower's operator states that the exterior cleaning cycle takes 3 to 4 months across close to 26,000 glass panels, each weighing 362 kilograms, and that the record height for facade installation on the project was 512 meters. 512 meters is not the top. The spire begins above that. Above the reach of the permanent access equipment, inspection means rope access technicians, or drones, or nothing. A rope access inspector working at that height is limited by wind, by heat, and by daylight, and a full visual survey of 650 feet of steel in those conditions is a campaign, not a routine. Drones have changed part of this in the last several years, and high-resolution photographic survey from an unmanned aircraft is now a normal tool on large structures. But wind at that altitude limits flying to a narrow set of days. The airspace over a city center is not casually available, and a photograph of a coating is not the same thing as a measurement of the steel underneath it. Ultrasonic thickness testing still requires a hand on the metal, and a hand on the metal at that height requires a person, a rope, a permit, and a day when the wind agrees to cooperate. I looked for a published inspection report on the condition of the steelwork in a supertall spire from any tower anywhere, and I could not find one. It is possible they exist and are simply not public, which would be entirely reasonable. If you have seen one, put a link in the comments and I will pin it. So what do engineers actually do about all of this? The first answer is to design the fatigue out rather than inspect it away. Members are sized so that the daily stress range sits well below the level where fatigue cracks initiate at all, which means the steel is heavier than strength alone would require. Fatigue is one of the few problems in engineering where the cheapest fix is to have solved it before the building opened. The second answer is damping. A slender tip can be fitted with a tuned mass damper of its own, a small one, tuned to the spire's frequency rather than the tower's. Taipei 101, which opened in 2004, made this idea visible to the public, with the large sphere hung near its summit, and the same principle scales down. The third answer is the shape of the tower underneath. The Burj Khalifa uses a stepped setback form that changes the width of the building as it rises. Because the vortex shedding rate depends on the width, a shape that keeps changing width never lets a single rhythm establish itself over the full height. The wind is broken up before it ever reaches the spire in an organized state. The fourth answer is monitoring in place of access. Strain gauges and accelerometers mounted during construction report continuously, and a change in the measured natural frequency of the spire is a signal that something in its stiffness has altered, long before anything is visible. Jeddah Tower in Saudi Arabia has been designed from the beginning with this assumption, because at its planned height, the inaccessible fraction of the structure is larger still. The National Institute of Standards and Technology and the Council on Tall Buildings and Urban Habitat have both pushed structural health monitoring as the practical answer for parts of buildings that human beings cannot easily reach. A visitor on the observation deck looks up at the spire and sees the last 100 meters of a photograph. The structural engineer looks at the same object and sees 4,000 tons of steel hanging off the end of a concrete cantilever in an environment with salt in the air, being cycled thermally twice a day, being struck by lightning several times a year, and being inspected by whoever is willing to hang from a rope in the heat. The facilities manager sits between those two views and has the least comfortable job of the three. He is responsible for a component that does not appear in the daily operating routine, has no scheduled downtime, generates no complaints, and produces no revenue. Every maintenance budget conversation he has about it is a conversation about spending money on something that is, by every visible measure, completely fine. What follows is a hypothetical engineering stress test. It is not a description or a prediction of an actual event at any specific tower. Imagine a July afternoon. The air temperature at ground level is over 110 degrees Fahrenheit, and the steel in direct sun is far above that, sitting at the top of its daily expansion. A thunderstorm is building offshore, which in the Gulf in summer means humidity climbing sharply while the surface stays hot. Now stack the rest of it. The wind ahead of the storm arrives at the particular speed that matches the spire's frequency, so the tip is already oscillating before the storm proper is anywhere near. A strike lands on the air terminal and dumps current down conductors that are already at their maximum thermal expansion. The rain front arrives 20 minutes later and drops the surface temperature of the exposed steel by 50 degrees Fahrenheit in a very short time, while the shaded faces cool much more slowly. And say, for the sake of the exercise, that a coating defect somewhere in the middle third of that steelwork has been quietly admitting moisture for a year, in a location that has not been visually inspected since it was built, because the equipment to inspect it does not exist on that building. How would anybody know? What signal would appear first, and who would be watching for it? Would a change in a natural frequency of a fraction of a percent be recognized as a warning, or filed as instrument drift? How long could that condition persist without producing anything a person on the ground could see? Those questions do have answers, and the answers are the reason none of this is a crisis. Fatigue design margins mean the daily cycling is happening at stress levels far below the initiation threshold, so a coating defect produces corrosion, not cracking, and corrosion at that rate is a decades-long process. Lightning current in a properly bonded structure travels through an enormous cross-section of steel and raises its temperature by a trivial amount. Continuous monitoring, where it is installed, is specifically designed to catch the slow change rather than the dramatic one, and the redundancy in a structure of that size means no single member is holding the spire up alone. The design is not fragile. It is operating in a place where nobody can look at it, and those are two entirely different statements that get confused with each other constantly. A structure can be conservative, redundant, and correctly detailed, and still be a structure whose actual present condition is an inference rather than an observation. Engineering is comfortable with that distinction. Most people are not, which is why the honest version of this story sounds more alarming than it is. Which brings back the picture that started this. The bolt of lightning coming out of the top of a Dubai tower is not an accident, and it is not a near miss. It is the visible half of a system that was designed to invite exactly that and to make it boring. The invisible half is what the same steel is doing on all the other days of the year, 5 inches at a time, in salt air, 650 feet above the highest point any maintenance cradle in the building can reach. A few things should be said plainly. Lightning protection, vortex shedding, and thermal cycling are general engineering phenomena, and the degree to which each one affects any particular structure depends on that structure's geometry, materials, coatings, and local climate. Nothing in this video asserts that any named building is currently experiencing a fault, a defect, or a deficiency in inspection. The stress test described near the end is a hypothetical illustration built from published principles, not a report of any real event. Any footage accompanying this narration is illustrative stock material and is not evidence of a problem in any structure. This is an educational discussion and is not a substitute for professional assessment. If you want to understand the hidden systems that keep enormous cities functioning, make sure to subscribe to the channel. And one question: have you ever seen the very top of a tall building being worked on by a person rather than a machine? Tell us which building and what they were doing in the comments below.